So in this video, we will talk about conditional probability. So conditional probability is the probability that an event occurs given that another event has already occurred. So it allows us to update probabilities when additional information becomes available. Now, mathematically, you have the formula to calculate conditional probability, and it's written as follows. So the probability of A given B. So in this case, the notations mean that I want to calculate the probability of the event A occurring given that the event B has already occurred. And this is equal to the probability of A intersect with B altogether divided by the probability of B. In this case, the vertical line means given. So A occurring given B has already occurred. And I just want to give you a quick recall that to calculate the probability of an event, what you do is you find fractions that is equal to the cardinality of the desirable outcomes over the cardinality of the total possible outcomes. So that is, I can actually rewrite this particular formula by doing the following manipulations. So I can turn the probability of A intersect with B in terms of cardinalities. That is, the numerator becomes the cardinality of A intersect with B divided by the cardinality of the sample space over the cardinality of B divided by the cardinality of the sample space. So we technically just apply the definitions of probability. Again, the probability of an event is equal to the cardinality of desirable outcomes over the cardinality of the total possible outcomes. Now, because you divide fractions, you're going to get the cardinality of A intersect with B over the cardinality of S times the cardinality of S divided by the cardinality of B. So what I did is, because again we divide fractions, that means you can multiply by the reciprocal. Then you cancel out the cardinality of S, and you arrive as an alternative answer to the probability of A given B. That is, the probability of A given B is equal to the cardinality of A intersect with B over the cardinality of B. So you can use either formula to calculate for the probability of A given B. So in this video, I'm only going to consider one example related to conditional probability. In the case that we are dealing with, is called the non-independent event. Then later, I'm going to give you another formula for the case of independent events. Then in the next videos, I'm going to give you more example related to conditional probability. So the first example I'm going to consider is that, so suppose you have a box that has 3 red marbles and 2 black marbles. Now you want to select 2 marbles, and you want to know what is the probability that the second marble is red given the first one is already red. So you let A to be an event of getting a red marble from the second draw. And B to be the red marble from the first draw. So what we want to do is you want to calculate the probability of A given B. So by definitions, you have the probability of A and B over the probability of B. So in this case, the interpretations is that you have the probability of B, which is the probability of getting a red marble in the first draw. And the notations P of A intersect with B means that this is the probability of getting red marbles in both draws. So I'm going to calculate the probability of B and the probability of A intersect with B. To calculate the probability of B, this is equal to the fractions of the number of desirable outcomes over the number of total possible outcomes. So in this case, the cardinality of B over the cardinality of S. So the cardinality of B is that what is the number of desirable outcome, that is getting the red marble in the first draw. So the problem gives you that there are 3 red marbles and 2 black ones. So you have 2 draws. So the first one, how many choices you have to get a red marble? So you have 3 choices. Now in total you have 5 different marbles. So in the second draw, this can be either the red one or the black one. We don't care at this point because we are calculating the cardinality of B. That means you just want to know the desirable outcomes. That is, the first draw is the red marble. Because you already get 1 red marble, you're left with only 4 marbles in total. So the second draw is 4. So this can be the red marble, this can be the black marble. And altogether, you have 3 times 4, which is equal to 12 desirable outcomes. Now, in the case of the cardinality of S, that means the number of the total possible outcomes. So again, you have 2 draws. In total, you have 5 different marbles. You have 5 different choices for the first draw. And now you're left with only 4 marbles. For the second draw, it doesn't matter red or black. The choice is going to be 4 as well. Then altogether, you get 5 times 4 number of outcomes. So the probability of B is going to be 3 times 4 over 5 times 4. You can cancel out the 4 here, and you're left with 3 over 5. So the probability of getting a red marble in the first draw is going to be 3 over 5. Now I'm going to move on and do the calculations for the probability of A intersect with B. So this is going to be equal to the cardinality of A intersect with B over the cardinality of S. So again, remember you also have 2 draws in this case. The cardinality of A intersect with B means that what is the number of outcomes where the first draw is red and the second draw is also red. Alright. So remember you have 3 different reds. So for the first draw, you have 3 different reds. And you left with only 2 reds in the box. So for the second draw, in order to get another red, there are 2 choices. So altogether, you have 3 times 2. And for the cardinality of S, which is the sample space, in this case, is similar to the calculations of the probability of B. So that is S going to be equal to 5 times 4. So again, let me go through that analysis one more time. So in total, you have 5 different marbles. The first draw gives you 5 different choices. Now you're left with only 4 marbles in the box. For the second draw, there are 4 different choices. So altogether, you get 5 times 4. So now you do the calculations and you get this is 6 over 20. Simplifying it down to 3 over 10. Therefore, the calculations of the probability of A given B is going to be equal to the probability of A and B over the probability of B. For the probability of A intersect with B is going to be 3 over 10 divided by the probability of B, which is 3 over 5. And because you divide the fractions, you can turn this into a multiplication of the reciprocal. So that is 3 over 10 times 5 over 3. This gives you 5 over 10, or 1/2 for that matter. So there is 50% chance of you getting the red marbles from the second draw, given the first draw also give you a red marble. And the problem we are working with, or the formula that we are dealing with, is the conditional probability for the case of non-independent events. So I'm going to go back here in the notes. So this is for non-independent event. So the events that we are dealing with in this particular cases, in this particular scenarios, are considered to be dependent to one another. Now I'm going to move on to another definition where the 2 events are independent from one another. So suppose you have 2 events A and B that are independent. means that the outcome of one event does not depend on the other or vice versa. Then you have the following formula, that is the probability of A intersect with B is equal to the probability of A multiplied with the probability of B. So consider the following example. You have two students in class. One is the student A and the other student is B. They'll both take a final exams on discrete mathematics, and the probability that A is going to pass is 70%, and the probability of B passes the test is going to be 95%. So I want to find the probability that A or B or both passes the exam. So I want to know what is the probability of A union with B. So by the addition rule of probability that we learned in the last lecture, you have this probability of A union with B is equal to probability of A plus the probability of B minus the probability of A intersect with B. So in this case, the intersections is not going to be the empty set because we want to know if both of them are going to pass the exam altogether, not separately. Therefore, by the independent event definitions, you're going to get that this is equal to the probability of A plus the probability of B minus the probability of A times the probability of B. And you know about probability of A, which is equal to 0.7. The probability of B is going to be 0.95 minus 0.7 times 0.95. And if you have a calculator, you're going to get that the probability of A passes the exam or B passes the exam is going to be. So I'm going to give you another examples to illustrate the concept of independent events. So let X and Y represent the outcomes of rolling two dice. So the event of getting a number on dice X has nothing to do with the event of getting a number on dice Y, because you can calculate the probability of getting a number on dice X independently from calculating the probability of getting a number on dice Y. So let's say you have part A, that is, you want to know what is the probability of the first die X is 1. So the probability of X equal to 1. So again, we're going to follow the definitions. That is the numerator equal to the number of desirable outcomes. So there is only one desirable outcome to get the face 1 on the die. Divided by the number of the total possible outcomes. So there are 6 faces on the die. Therefore, the total possible outcomes is going to be equal to 6. So the probability of getting a 1 on the first die X is going to be equal to 1 over 6. So the next question is, I want to know what is the probability that both X and Y are equal to 1. So that means I want to find the probability of X equal to 1 and the probability of Y equal to 1. So these two events are completely independent from one another. Therefore, this is equal to the probability of X equal to 1 times the probability of Y equal to 1. And the probability of X equal to 1 we already found, which is equal to 1 over 6. And the probability of Y equal to 1, because it's going to be a similar die, and they have 6 faces on a die, and similar calculations going to be for the probability of Y equal to 1. Therefore, the probability of Y equal to 1 is going to be also 1 over 6. And this gives me 1 over 36 for the answer in the case of finding the probability that both X and Y are 1. So that's it for this video. In the next video, I'm going to spend time doing some example related to conditional probability.